The issue described is most likely caused by an improper grounding system, resulting in a condition known as stray voltage. Stray voltage occurs when electrical current finds an unintended path to ground through conductive materials such as water pipes or metal fixtures. It can result from a faulty electrical wiring system, damaged insulation, or improper grounding. Several factors could be contributing to this situation. Firstly, a faulty grounding electrode system, GES, may be inadequate or not properly connected to the water pipes. Secondly, the damaged BX cable is likely a significant source of stray voltage. The exposed conductors are making contact with the water pipes, transferring electrical potential. Thirdly, galvanic corrosion might be a factor. The dissimilar metals of the water and gas pipes can create an electrochemical reaction, leading to galvanic corrosion and increased conductivity. To address this issue, several troubleshooting steps should be taken. 1. Isolate the affected area by disconnecting the damaged BX cable completely from the electrical system. 2. Inspect the grounding electrode system and ensure it is properly installed and connected to the water pipes. 3. Test for stray voltage. Use a voltmeter to measure the voltage between the water pipes and a known ground point, such as the bare copper wire in the grounding electrode system. There should ideally be no voltage present. 4. Inspect water and gas lines. Check for damage or corrosion on the water and gas lines. Consider using a voltage detector or contacting a plumber or gas fitter for a thorough inspection. 5. Install a grounding rod. If the grounding electrode system is inadequate, install a ground rod near the affected area to provide a better ground path. 6. Rewire the affected circuit. Replace the damaged BX cable with a new one and ensure it is properly grounded to the junction boxes. Some additional considerations include: firstly, the voltage present on the water and gas lines is likely low, but it could still be hazardous. Secondly, contact a qualified electrician to ensure the safety of the electrical system. Thirdly, inform the homeowner about the potential hazards of stray voltage and the importance of regular electrical inspections. A more in-depth explanation of each of the considerations is as follows. Stray voltage is a phenomenon where a small voltage exists on metal objects not designed to carry electricity. This can occur due to various reasons, primarily related to grounding and wiring issues. When an electrical system is properly grounded, any stray current should flow back to the source through the grounding path, preventing it from accumulating on other metal objects. However, if the grounding is inadequate or faulty, the current can find alternative paths, such as through water pipes, gas lines, or metal fixtures. This can lead to a voltage potential on these objects, which can be felt as a mild shock when touched. Several factors can contribute to stray voltage, including damaged or deteriorated wiring, loose connections, improper grounding, and electrical imbalances within the system. In older homes, such as the historical bed and breakfast mentioned, the wiring may be outdated or damaged, increasing the risk of stray voltage. Additionally, modifications or additions to the electrical system over time may have compromised the original grounding scheme. Galvanic corrosion can also play a role in stray voltage. When dissimilar metals are in contact, such as copper pipes and steel gas lines, an electrochemical reaction can occur, leading to corrosion. This corrosion can create a conductive path for stray current, further exacerbating the problem. Therefore, understanding the causes and effects of stray voltage is crucial for ensuring electrical safety. The first step in addressing stray voltage is to identify the source of the problem. This involves a systematic inspection of the electrical system, including the grounding electrode system, wiring, and connection. A qualified electrician can use specialized equipment to measure voltage potentials and trace the flow of current to pinpoint the source of the stray voltage. Once the source is identified, appropriate corrective measures can be taken. This may involve repairing or replacing damaged wiring, tightening loose connections, improving the grounding system, or addressing galvanic corrosion. In some cases, it may be necessary to install additional grounding electrodes to provide a more robust grounding path. In addition to addressing the immediate problem, it's important to take preventive measures to minimize the risk of future stray voltage issues. This includes regular electrical inspections to identify and correct any potential problems before they become hazardous. Homeowners should also be educated about the dangers of stray voltage and the importance of proper grounding. By taking these steps, it is possible to create a safer electrical environment for everyone. Here are some specific steps that a homeowner or electrician can take to troubleshoot and resolve stray voltage issues. Firstly, inspect the grounding electrode system. The grounding electrode system, GES, is a critical component of the electrical system that provides a path for stray current to flow back to the source. The GES typically consists of a ground rod, ground plate, or metal water pipe that is connected to the electrical panel with a grounding wire. Inspect the GES to ensure that it is properly installed and in good condition. Look for signs of corrosion, damage, or loose connections. If the GES is inadequate or damaged, it may need to be repaired or replaced. Secondly, check the wiring and connections. Inspect all wiring and connections in the affected area for signs of damage, deterioration, or loose connections. Pay particular attention to wiring that is exposed to moisture or physical stress. Replace any damaged or deteriorated wiring and tighten any loose connections. Thirdly, test for stray voltage. Use a voltmeter to measure the voltage between various metal objects in the affected area and a known ground point, such as the bare copper wire in the GES. If any voltage is detected, it indicates the presence of stray voltage. The voltage should ideally be 0. Fourthly, isolate the affected circuit. Turn off the circuit breaker that supplies power to the affected area and repeat the voltage measurements. If the stray voltage disappears when the circuit is turned off, it indicates that the problem is within that circuit. Fifthly, trace the source of the stray voltage. Once the affected circuit has been identified, trace the wiring to pinpoint the source of the stray voltage. Look for any potential sources of stray current, such as damaged wiring, loose connections, or appliances with faulty insulation. Sixthly, correct the problem. Once the source of the stray voltage has been identified, take appropriate corrective measures to eliminate it. This may involve repairing or replacing damaged wiring, tightening loose connections, improving the grounding system, or replacing faulty appliances. Lastly, verify the repair. After completing the repairs, repeat the voltage measurements to ensure that the stray voltage has been eliminated. If the stray voltage persists, it may be necessary to consult with a qualified electrician to further investigate the problem. Additionally, here is more information about grounding electrode systems. The grounding electrode system, GES, is a critical component of an electrical system, designed to provide a low impedance path for fault current to return to the source. This system is essential for safety, as it helps to prevent electrical shock and minimize the risk of fire in the event of a ground fault. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes, connected to the electrical system's grounding busbar or neutral point via a grounding electrode conductor. The primary purpose of the GES is to establish a connection to the earth, providing a reference point for the electrical system voltage. This connection helps to stabilize the system voltage and limit the potential difference between conductive objects and the earth. In the event of a ground fault, where a live conductor comes into contact with a grounded object, the GES provides a low impedance path for the fault current to flow back to the source. This high current flow will typically trip a circuit breaker or fuse, quickly disconnecting the power and preventing further damage or injury. The effectiveness of the GES depends on several factors, including the type and number of grounding electrodes, the soil resistivity, and the quality of the connections. The National Electrical Code, NEC, specifies the requirements for grounding electrode systems, including the types of electrodes that are permitted, the minimum size of the grounding electrode conductor, and the bonding requirements for metal water pipes and other conductive objects. Ground rods are a common type of grounding electrode, typically consisting of copper or copper-clad steel rods driven into the earth. The NEC requires that ground rods be at least 8 feet long and 5/8 inch in diameter. In some cases, multiple ground rods may be required to achieve the desired grounding resistance. Ground plates are another type of grounding electrode, typically consisting of copper or zinc-coated steel plates buried in the earth. Ground plates provide a larger surface area than ground rods, which can be beneficial in areas with high soil resistivity. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. The NEC requires that metal water pipes be bonded to the electrical system's grounding busbar or neutral point. The grounding electrode conductor is a wire that connects the grounding electrode to the electrical system's grounding busbar or neutral point. The NEC specifies the minimum size of the grounding electrode conductor, which depends on the size of the service entrance conductors. Bonding is the process of connecting metal objects together to create a continuous electrical path. Bonding helps to minimize the potential difference between conductive objects, reducing the risk of electrical shock. The NEC requires that all metal water pipes, gas pipes, and other conductive objects that are likely to become energized be bonded to the electrical system's grounding busbar or neutral point. Regular inspection and maintenance of the grounding electrode system is essential to ensure its continued effectiveness. Grounding electrodes should be inspected for corrosion, damage, and loose connections. The grounding electrode conductor should be checked for proper size and condition. Bonding connections should be inspected for tightness and corrosion. If any problems are found, they should be corrected immediately. The electrical system in the historical bed and breakfast could benefit from an updated and properly installed grounding electrode system. The stray voltage found is a serious issue that needs to be addressed for the safety of the inhabitants. Finally, galvanic corrosion is an electrochemical process that occurs when two dissimilar metals are in electrical contact in the presence of an electrolyte, such as water or soil. This process can lead to the corrosion of one of the metals, while the other metal is protected. Galvanic corrosion is a common problem in many industries, including plumbing, construction, and marine engineering. When two dissimilar metals are in contact in the presence of an electrolyte, a galvanic cell is formed. The more active metal acts as the anode, where oxidation occurs and the metal corrodes. The less active metal acts as the cathode, where reduction occurs and the metal is protected from corrosion. The rate of galvanic corrosion depends on several factors, including the difference in electrochemical potential between the two metals, the conductivity of the electrolyte, and the temperature. Metals can be ranked in terms of their electrochemical potential using a galvanic series. The galvanic series lists metals in order of their tendency to corrode in a specific environment. Metals that are higher in the galvanic series are more active and more likely to corrode than metals that are lower in the galvanic series. The electrolyte plays a critical role in galvanic corrosion. The electrolyte provides a medium for the flow of ions between the anode and the cathode. The conductivity of the electrolyte affects the rate of galvanic corrosion. Higher conductivity electrolytes will promote faster corrosion rates. Temperature also affects the rate of galvanic corrosion. Higher temperatures generally increase the rate of corrosion. Galvanic corrosion can be prevented or mitigated by several methods, including firstly, selecting compatible metals. When designing a system, it is important to select metals that are close together in the galvanic series to minimize the potential for galvanic corrosion. Secondly, insulating dissimilar metals. Insulating dissimilar metals from each other can prevent electrical contact and reduce the risk of galvanic corrosion. This can be achieved by using non-conductive materials, such as plastics or rubber, to separate the metals. Thirdly, using sacrificial anodes. Sacrificial anodes are made of a more active metal than the metals being protected. The sacrificial anode corrodes instead of the other metals, protecting them from corrosion. Sacrificial anodes are commonly used in marine applications to protect ship hulls and other metal structures from corrosion. Fourthly, applying coatings. Applying coatings to the metal surfaces can provide a barrier between the metal and the electrolyte, reducing the risk of galvanic corrosion. Coatings can be metallic, organic, or inorganic. Fifthly, controlling the environment. Controlling the environment can also help to prevent galvanic corrosion. This can be achieved by reducing the humidity, temperature, or salinity of the environment. In plumbing systems, galvanic corrosion can occur when dissimilar metals, such as copper pipes and steel pipes, are connected. This can lead to the corrosion of the steel pipes, resulting in leaks and other problems. To prevent galvanic corrosion in plumbing systems, it is important to use dielectric unions to separate the dissimilar metals. Dielectric unions are fittings that contain a non-conductive material that prevents electrical contact between the metals. In addition to dielectric unions, other methods can be used to prevent galvanic corrosion in plumbing systems, such as using compatible metals, applying coatings, and controlling the environment. In the case of the historical bed and breakfast, galvanic corrosion could be contributing to the stray voltage problem. The dissimilar metals of the water and gas pipes could be creating an electrochemical reaction, leading to galvanic corrosion and increased conductivity. This corrosion could be providing a path for stray current to flow, exacerbating the stray voltage issue. This is in addition to the BX cable and its condition. To address this issue, it may be necessary to replace the dissimilar metals with compatible metals or to install dielectric unions to separate the metals. It is also important to ensure that the grounding system is properly installed and maintained to provide a low impedance path for fault current to return to the source. This will help to minimize the risk of stray voltage and galvanic corrosion. When dealing with electrical issues, especially in older buildings, it's crucial to prioritize safety and seek the assistance of qualified professionals. Ignoring these issues can lead to dangerous situations, including electrical shocks, fires, and damage to property.